Hi, I'm Rick Becker, speaking to you from the Statistics Lab at AT&T Bell Laboratories. In the next few minutes, you're going to see some computer-generated displays of data, dynamic graphics, data in motion. Of course, pictures of data have been around for well over 200 years. And computer-generated pictures of data have been with us for at least 20 years. However, the kinds of graphics displays that we're about to show you have, until very recently, only been available in research institutions. The revolution in computing, where each year more power has been available at lower cost, has changed all that. The kinds of displays we're about to show are available now on equipment at relatively modest prices. Let's begin by looking at data on 1979 automobiles. Consumer Reports, in their annual automobile issue, gave information in April of 1979 on a number of different 79 models, including things such as weight, price, repair records, and much more. At the same time, the Environmental Protection Agency gave gas mileage figures for a number of those same cars, and by combining those two pieces of information, we can get a look at the relationship between weight and gas mileage. If we produce a plot that shows weight along the horizontal axis, miles per gallon on the vertical axis, we can plot points, one for each car, like this. For example, we have an AMC Concorde that weighs 2,930 pounds and gets 22 miles per gallon. Right there. The BMW 320i weighs 2,650 pounds and gets 25 miles per gallon here. And we can do the same thing for the entire set of 74 automobiles. We'll end up with the following plot. Of course, with modern computers, we can do the same plot much faster. Anyone would prefer having the computer do the work. However, there was really an advantage to doing the plot by hand. When we worked by hand, we had a close relationship with the data, and we would tend to know points that fell away from the other points, and we could identify particular automobiles, especially those outliers. Fortunately, we can have that same kind of advantage when using our computer terminal. We can use a mouse, which rolls about on the table and positions a cursor at corresponding points on the screen. This particular mouse has 3 buttons, which can be pressed to signal the computer to do something. On this plot, we've arranged for the cursor to be surrounded by a diamond. As we roll around on our computer-drawn scatter plot, the car names pop up whenever the diamond covers their points, and disappear when the diamond moves on. If we hold down the leftmost mouse button, the labels stay even when the diamond leaves. The middle button erases a selection, while the rightmost button allows us to change the size of the diamond from very small to large, wherever we'd like. Using this tool, we can get to know which cars behave in a way different from a majority of the others. For example, the Olds 98 and the Cadillac Seville seem to have much higher gas mileage than would be predicted based on their weight, whereas Volkswagen Rabbit, Subaru, and Datsun 210 are some of our highest mileage cars. You might wonder why we didn't just put all of the labels on to begin with. Does this answer your question? Our plot seems to show that there's a fairly strong relationship between auto weight and mileage. We can superimpose a mouse-controlled line on the scatter plot to see if the relationship seems to be linear. Again, the mouse allows us to interact with the display. This time, the mouse moves the line about the screen while the buttons rotate the line left and right. No single line fits our data very well. The points on the plot appear to curve. We can even deposit lines fit to the low weight cars and the higher weight cars and see two relatively different slopes. Perhaps a power transformation would help our data look more linear. A power transformation re-expresses the data so that instead of using weight, we might use weight squared, the square root of weight, or the logarithm of weight. Another high interaction technique will allow us to see just how much effect power transformations can have on a scatter plot. The numbers at the top of the plot show the powers that we will use to transform the numbers on the x and y axes. When we see the numbers 1 and 1, we have the original data. You can see how much effect these transformations can have on equally spaced linear data. As I move horizontally, only the x powers change. As I move vertically, only the y powers change. We can apply a power transformation to our automobile data. Instead of plotting weight on the horizontal axis, we'll plot a power of weight. And of course, we could also transform the y-axis. Here's our familiar plot again. Watch what happens as we use the mouse to change the powers. Notice how the plot, which shows the y-axis power as -1, looks quite linear. As a matter of fact, the -1 power is the reciprocal, which corresponds to expressing mileage as gallons per mile rather than miles per gallon. So, let's go back to a basic scatter plot with weight on the horizontal axis, but this time using gallons per 100 miles on the y-axis. As we expected, the data points now fall roughly on a straight line. It makes sense then to fit a straight line to the data. We do this using the well-known least squares technique, which chooses a line that is as close as possible to all of the data points simultaneously. The fit looks reasonable. However, it might be interesting to see what would happen to the line if perhaps one of our data points were to change. For example, suppose the Lincoln Continental, our heaviest car, were able to achieve 20 or even 50 miles per gallon. On this plot, that's 5 or 2 gallons per 100 miles. Again, we can use the mouse to provide the interactive control necessary to pick up the data point and move it. All the while, the fitted regression line continues to move as a single data point moves. Notice that the line is quite sensitive to changes in the mileage of the Lincoln, but is affected very little by changes to a car like the AMC Concorde. You're seeing an example of the concept known as leverage. A very light or very heavy car is able to influence the fitted line much more than one that is middleweight. What do you think would happen to the line if the Honda Civic, our lightest car, turned out to be a gas guzzler? Right. The line will move quite a bit. Up to now, we've been looking at two variable data. We've plotted weight and miles per gallon. But there are many other characteristics of automobiles that might also be very interesting to plot. For example, price. We might like to produce a scatter plot that shows simultaneously weight, miles per gallon, and price. In that case, we'd have a plot that had length, width, and height. Of course, three-dimensional objects like this are very familiar to us. We have three-dimensional houses and cars of our very own. We can look at real objects from a variety of viewpoints. Rotating an object helps to convince us that it's really three-dimensional and not just a flat painting. Our eyes pick up the relative motion of parts of an object, and our brains translate that information into a sense of three dimensions. In this same way, we can have our computer help us look at models of real objects by giving us different views in quick succession to simulate motion. Although our computer screen is flat, motion can give us the feeling of three dimensions. How does this rotation help us to understand our data? Well, unlike cars and houses, our data doesn't consist of solid objects like walls and tires, but rather it's points, one for each car plotted in space. Here we have miles per gallon, weight, and price, and each little bulb represents one automobile. If we look from the top, we have a view much like our original scatter plot. But we can also look at the model from many other angles. Here is a side view showing price and weight. Another side view can show price and miles per gallon. Now, as we continuously move around, we begin to see some of the three-dimensional relationships in the data. For example, price seems to follow weight to a large extent. The heavier cars are usually more expensive, the lighter cars tend to be less expensive. Just as the computer was able to rotate a model of our house, it's also able to rotate a model of our data. Here we see weight horizontally and price vertically. As we rotate, we can end up with miles per gallon horizontally and price vertically. Notice that we can freeze the action at any time. We're also in control of the angle and the speed of rotation. Having the computer draw the picture is much easier than constructing a physical model. We can usually see the same kinds of relationships in our computer-drawn picture as we could from looking at the model. Let's take a moment and go back to our house. Architects have a way of dealing with three-dimensional objects. They typically do it by drawing various views. For example, they may have a front view, a side view, and perhaps even a top view of the same object. When these views are combined, especially if they're pasted on the surface of a cube, as we've done here, it's fairly obvious that these all show different views of the same three-dimensional object. We can even unfold our cube and show the three related views. Just as we did with our house, we can show our scatter plot of car data on the surface of a cube. Here, for example, is the side that shows weight and miles per gallon. Over here, we have price and miles per gallon. And on top, weight and price. And as we did with the house, we can unfold this to produce a view showing the three scatter plots simultaneously. We call this view a scatterplot matrix. The layout of our scatterplot matrix is important. Looking across the first row, we always see weight on the vertical axis. Looking down the third column, miles per gallon is always on the horizontal axis. One problem with the scatterplot matrix is that it is sometimes difficult to identify a single point on several plots. Our high interaction technique solves this problem by highlighting on all the scatter plots any point inside the rectangular region. The rectangular region controlled by the mouse is known as a brush because it can be used much like a paintbrush. See how a set of points can be painted? Even though the brush is rectangular, there's no restriction on the shape of the data regions that can be painted. And unlike a normal paintbrush, our computer-driven brush can also erase. By using a pop-up menu, we can control other aspects of the brushing process. Instead of highlighting points, we can delete them. Suppose, for example, we didn't want to consider any of the higher-priced cars. Once we get rid of the unwanted points, we can rescale the data so that the points once again fill the plots. We can also identify specific points. But suppose we'd want to do the opposite operation. For example, we may want to locate the Honda Accord on the plot. By using another pop-up menu, we can select the Accord. And once we've done this, its point is highlighted on the scatter plot. The size of the rectangular brush can also be changed by the user. A small brush can be useful for identifying areas with dense points. Notice how our Honda Accord is the one that was highlighted. Our data sources give us many more measurements on automobiles other than just price, weight, and miles per gallon. We have things such as length, engine displacement, gear ratios, and turning radius. The Scatterplot matrix technique gives us a way to go beyond the limitations of three-dimensional models and allows us to look at much higher dimensional data. Let's look at how the Scatterplot matrix technique can be used with seven-dimensional data. You see here a Scatterplot matrix showing price, miles per gallon, weight, length, turning circle, engine displacement, and gear ratio. There are a total of over 3,000 points on this Scatterplot matrix. And even at that, we can still see the familiar configuration of our miles per gallon weight Scatterplot. We've seen a number of dynamic techniques for displaying data in the past few minutes. Dynamic labeling, power transformations, regression leverage, rotating point clouds, brushing a Scatterplot matrix, pop-up menus. By now, you can appreciate how valuable these dynamic graphics displays can be for the data analyst. I hope you've enjoyed our presentation.
Thank you.